I have 1 week to learn everything I can about physics simulations and games by coding my own engine from scratch. Physics engines are the core to games like World of Goo, Unravel, The Floor is Jelly, Line Rider, and a casual game that I play literally every day, Skate or Don't. So in this video, I will attempt 10 stages of difficulty using just simple intuition and one easy math concept. The goal? To recreate my favorite game in my brand new, homemade physics engine. So the foundation of everything I'm going to do starts here at level 1. I just have to make a bouncing ball. I've done this a million times, so we'll fly through this one. It starts with a circle, and it has a position, a size, and of course a speed. To simulate the circle moving, we just add the speed to its position every frame. And then we run that at like 60 frames per second, and now we've got movement! We'll make it bounce off the sides of the screen before inventing gravity. So for the ground, you'd think the best way to do this would be to, say, if the circle's Y position is below the ground, minus the radius of the ball, then just reverse its Y speed, right? You'd think so, but if I place things just right, it does this. Why? Well, because numbers in computers are not precise, and in this very specific case, if you add 4.1 to the position here, and then subtract 4.1 on the way back up, a tiny precision error causes the circle to still be underground, and it just keeps reversing its speed forever. Not what we want. Well, I'm mentioning this now because in Infinite Bounce, one of my first games I made when I was 12, I used this exact same logic, and I was always so confused why this happened on some levels. The circle would just sometimes stick to a wall out of nowhere. Well, now I know. But this will happen even more when we add gravity and friction, so we do need to fix this issue now. We'll just only detect the collision if the circle is moving towards the ground. We can also force the circle to be above the ground when it collides, and that should fix the issue. When I made Infinite Bounce, I had no idea how to add angled walls, but that's because I didn't know about the most overpowered formula in physics simulations, dot products. Oh, how I love dot products. In games, this simple formula helps calculate collisions, make shadows, shade objects, create reflections. It's used everywhere, because just look at it, it's so simple. x1 times x2 plus y1 times y2. That's it. This is how I visualize a dot product. First, I imagine an arrow placed in the center of space, pointing in some direction. It always has a length of 1. Then, I imagine a second point in space, and what the dot product tells me is, how far in the direction of the arrow is this point? Like, if the arrow is pointing straight up, it tells me how high up the point is. If the arrow is pointing to the side, the dot product tells me how far in that direction the point is. So if we place the arrow pointing away from the ground, suddenly we know exactly how far away our point is from the ground, no matter what angle it's at, thanks to dot products. And this arrow is called the ground's normal vector. So now we can detect when a circle is close enough to the ground to collide using a dot product. To make it bounce in the right direction, we just need to look at how much of the circle's speed is going in the normal direction and how much of it is sliding along the ground. Hey, look, more dot products. Okay, we just reverse the part going in the normal direction and do nothing with the part that's going in the sliding direction. Or, well, we can reduce it a little bit due to friction. Then we just throw in a little gravity to the vertical speed and reduce the bounce speed by some percentage so it loses energy over time. We'll call this restitution because we're fancy like that. A high restitution is like a bouncy ball. It keeps almost all of its energy. And low restitution is kind of like a hacky sack where it loses everything to sound and heat. Perfect collisions with angled walls. Take that, 12-year-old me. And 13-year-old me who tried again, but gave up and turned the broken physics into a sponge. This was my screensaver era. The sponge is a screensaver. All right, but what about bouncing off of corners? I mean, this is the last piece needed for a circle to bounce off of any shape. And my approach is to split each shape into individual line segments, and then split each line segment into 3 sections. The middle part can be handled just like we did in level 2, and then the trick with the end pieces is that the normal direction is literally just pointing in the direction of our circle. All we have to do is detect which piece of the line segment the circle's in. In other words, its distance along the line. In other words, we take the dot product. If the dot product is negative, we're on one end, and if it's between 0 and the length of the line, it's in the middle part. And if the dot product is bigger than the length of the line, we're on the other end. Now we can have any shape we want. And it works way better than my attempt when I was 16 years old, which moves the ball in the normal direction rather than correctly bouncing across it. Look, I didn't know about dot products back then. How could I have possibly conquered level 3 physics without that knowledge? Circles still aren't colliding with each other. When circles collide, the first thing we'll notice is that their normal direction is just the distance between them. That's pretty simple. Using our normal direction and sliding direction, we can get how much of the speed goes into the bouncing and how much goes into the friction. Instead of the circle reflecting its own speed, though, we need to consider the relative speeds between the two circles. Think about it. If a circle is not moving, but it gets hit by another one coming in really fast, if we subtract the relative speed between them, the fast circle stops and the stationary circle takes all the speed, just like in real life. This is called an elastic collision. Some collisions are less elastic, and instead of bouncing, they'll just kind of stick to each other more. They both end up with the average speed of the two. So we can implement both of these collision types and then have restitution be the slider between the two. Oh, and this code reduces down nicely if you prefer that. We should now have circle collisions. If you look really closely, you can see that they're squishing together weirdly. We can fix that. Instead of running the simulation at 60 FPS, we'll run it at literally 20 times faster. And there we go, way more stable. When we can connect two circles with a spring, suddenly that unlocks objects and structures, ropes and cloth simulations, and way more. And it's surprisingly super easy. I have a new spring class that takes in two circles and a target length. Every step of the simulation, we just propel the objects closer to that target length. I got the best results by not just using the circle's position for this, but their predicted position 10 steps ahead. This helps prevent the spring from overshooting and vibrating out of control. There's probably a better way to adjust that, but this works fine for me at least. Game dev is an art, after all. We can now connect circles with springs to create ropes, and it all just kind of works. It's how I made those tree animations in my PowerPoint video, and in a way how I created wetclap.com. Except that's only in one dimension, not 2D. And in the intro music of this very video, I used a new plugin called Anukari, which runs a spring simulation to create sounds. It's so cool. If you add structural support beams inside of the object, instead of it being like a cloth, it becomes a soft body. There's really nothing new to code here. We can just model a cool looking shape and let it loose in zero gravity to see it bounce around. Basically, our physics simulation is at the point where it can do a lot of fun stuff just by us tweaking values and combining elements in creative ways. One creative thing we can do is make new points grow in between existing links. This is called differential growth, and it can create some really organic looking structures. Here are some things that I made using differential growth in the past. I'm not sure if any games actually use this specific concept, but hey, if no one else will, maybe I should. Now, I want to tackle something that I've never succeeded at before: rigid body collision. The last time I tried, it looked like this. I gave up really quickly. Since then, I've often heard of an algorithm called separating axis theorem, which can detect collisions between convex shapes, meaning shapes that don't have indents. The idea is, for every side of the two objects, you cast their shadows onto its normal direction, using dot products. If you can find a side where the shadows don't overlap, then the objects aren't colliding. But if you can't find one, then the side where the objects are overlapping the least, that's generally the side where the collision's happening. Then, to find the exact point where they're colliding, well, I actually had a really hard time with this, so for now I just picked the closest point that both shapes share, using a dot product. What followed were hours and hours and days of debugging, flipping random signs, realizing I implemented collision detection wrong, and generally getting so confused about what in the world was happening with these poor shapes. And finally, I ended up with, well, a half-baked solution that is still wrong. But hey, way better than my last attempt, so take that, 19-year-old me. The good news is, I don't really need perfect rigid bodies to make an homage to my favorite game. In this level, I'll recreate the skate or don't player controls. The skater character is a set of circles connected with springs. We can make a simplified version of it using 2 connected circles as the skateboard, connecting them together to form legs, and then supporting the torso with invisible springs. Same thing with the head. The arms are really interesting because in the original game, they can either be in the up position or the down position. To replicate this, I took inspiration from compliant mechanisms like the hinge on the ketchup bottle. So there's an invisible node that the hand is linked to, and the hand is in a stable state when it's either above or below it. Nice. Finally, I added controls, which affects the various spring lengths, so you can lean, crouch, and jump. Whee! Can you make it to the top of my obstacle course? It's frustratingly inconsistent and poorly designed. So in the past week, I already made it further into physics simulations than I ever had before, by a lot. But I know there's so much more to explore. Alex Austin, the developer of Skate or Don't, has specialized in making games with physics simulations for decades. He made 3D human simulations and vehicle controllers, added the Magnus effect for better golf ball simulation, coded physics for multiplayer, and made the world's first bridge building game. He's a legend! And yet, early on, he mentioned being frustrated by the rotations of rigid bodies. We all start somewhere, and while I could have just plopped in someone else's physics simulation code, like using Box 2D, I wouldn't have gotten the opportunity to walk the path of one of my heroes, and I think that's pretty valuable. Subscribe, check out my Patreon, and I'll see you next month. Bye! Man, do I love dot products. Whoa!